In this video, we're going to cover everyone's favourite topic, polynomial division. We're going to cover how do we actually perform polynomial division, and we're also going to look at a few ways in which we can make the process much easier for us, including how to shortcut the process entirely by equating coefficients, as well as how to use the remainder and factor theorems. Let's get to it. One way to simplify polynomials is to use polynomial division. Suppose you are told to simplify the following polynomial. Notice how f of x is actually a division of two polynomials. This is a hint that we can use polynomial division to achieve this simplification. So how do we actually perform polynomial division? Well, here's the step-by-step process. Let's run it. Using the example from before, set up the division as shown. The first step is to divide the highest order term of the numerator by the highest order term of the denominator. In this case, we end up with x squared. Step 2 is to multiply our result from step 1 by the entire denominator. Step 3 is to subtract the result from step 2 from our numerator. This result will then become our new numerator. Now, we're going to repeat steps 1 to 3 until there are no more x terms in our numerator. Again, I want to highlight that every time we run through this process, we're going to get a new numerator that is lower order than the numerator before it. So if we keep doing this process, eventually we're going to get to a point where there are no more x terms in the numerator. So we're going to go back to step 1 and perform the division. Then we multiply through and perform the subtraction. The numerator still has x terms in it, so we're going to perform the process again, until finally the numerator has no more x terms in it. We can now move on to the final step, which would be to express the remainder as a fraction. In this case, we have no remainder because the division was perfect. But if we did have a remainder, we would express it in the form n of x divided by d of x. So finally, if we go back to the start, we can actually express this entire polynomial as a simpler polynomial, x squared minus x minus 12. So that was a pretty lengthy process. Let's look at another way we can do this. First, you need to understand that we can solve polynomials by equating coefficients. Suppose we have the two polynomials f of x and q of x. If these two polynomials are equal, then it simply means that both polynomials are the same equation. And the only way they can be the same equation is if the coefficients of each term are identical. Hence, we can go term by term and solve for the missing coefficients. Let's start with the highest order term, x cubed. If we equate the coefficients, we'll see that 4x cubed equals ax cubed. We can see that a must equal 4. So what do we do about x squared? Well, we can see that it's absent from the first polynomial. In other words, it means its coefficient must be 0. Hence, we'll have 0 equals bx squared, so b must be 0. We can now show that f of x must equal q of x by substituting in our solution. Yeah, that's great and all, but what does this have to do with polynomial division? Allow me to demonstrate. The first thing to realise is that every time we perform polynomial division, we'll get a polynomial as a result. Hence, we can write the following. We also need to account for the possibility of a remainder term. So we'll just tack on this r at the end. Here's the cool part. Since we know the numerator and denominator polynomials, we can solve for the result after division p of x by equating coefficients. We're going to use the same polynomial that we used in the polynomial division process. We start by identifying the numerator and denominator. Fairly straightforward. Now, we need to write the general form of the polynomial p of x. We only need to write this polynomial up to the second order. This is because when you divide a third order polynomial by a first order polynomial, you get a second order polynomial. Next, we'll substitute and expand the equation as follows. We then simplify the right-hand side by collecting all the coefficients of each term. Finally, we can equate the coefficients to solve for p of x. Starting with the x cubed term, we have the following. Now for x squared, now for x, and finally for the remainder. If we plug these terms back into p of x, we can say that the division between n of x and d of x produces the result x squared minus x minus 12, which is actually the same result that we got when we did the polynomial division. Pretty cool, right? If we're only interested in the remainder after division, we don't need to go through any of those processes to find it. We can use the remainder theorem. It's worth noting that the remainder theorem only applies when you're dividing by a linear polynomial, or in other words, a first order polynomial. For example, suppose we have the following function f of x. We can find the remainder after division as follows. After we substitute in the terms, we'll find that the remainder is 6. Similarly, we can prove that a linear polynomial is a factor of another polynomial by using the factor theorem. For a polynomial to be a factor of another polynomial, the remainder after division must be 0. And we can get that remainder from the remainder theorem. So we can say that d of x is a factor of f of x if the remainder theorem gives 0. For example, we can show that x plus 1 is a factor of f of x as follows. The remainder theorem gave 0, thus x plus 1 must have been a factor. If you found this video helpful and would like to see more, I actually have a Google Drive with written versions of these lectures covering the entire Year 12 Math Methods syllabus. I've made these resources available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.